Online Analyzer Tutorial Part 6. Analyzer House Protection. Overview and Objectives. Analyzer house protection is a critical aspect of ensuring operational safety, personnel protection, and the longevity of sensitive analyzer equipment. These protective measures are designed to prevent, detect, and respond to abnormal conditions that could pose risks such as fire, explosion, equipment damage, or health hazards. A properly protected analyzer house supports continuous, reliable analyzer operation while meeting the safety and regulatory requirements of hazardous industrial environments. Protection systems must be integrated into the analyzer house from the design phase and must include provisions for fire detection and suppression, gas detection, emergency shutdowns, safe electrical isolation, overpressure monitoring, and alarm annunciation. These systems work collectively to mitigate risks arising from process gas leaks, ventilation failures, power loss, or external hazards. Gas detection and response. Gas detection is a cornerstone of analyzer house safety. Detectors must be installed to identify the presence of flammable gases, e.g. methane, hydrogen, VOCs, and toxic gases, e.g. H2S, CO, within the enclosure. Sensors should be located near potential leak sources such as sample handling panels, analyzer inlets, or vent connections. Gas detectors must be integrated into an automated safety response system. When gas concentrations exceed predefined alarm thresholds, e. 20% and 60% of the lower flammable limit, the following actions are typically required. Activate visual and audible alarms inside and outside the analyzer house, automatically de-energize non-intrinsically safe electrical systems, trigger ventilation system override to increase fresh airflow, close isolation valves on sample lines if applicable, transmit alarm signals to the plant's DCS or safety system. Calibration and testing of gas detection systems must be performed at regular intervals to maintain reliability and compliance with international standards, such as IEC 6079-29-1 and IEC 6079-29.2 for flammable gas detection in industrial applications. Fire detection and suppression. Fire detection systems should include smoke detectors, heat detectors, or flame detectors, depending on the risk assessment. Detectors must be chosen based on analyzer house size, airflow patterns, and equipment layout. The system must initiate local and remote alarms and may also trigger suppression systems or electrical isolation if required. For suppression, options include portable fire extinguishers suitable for electrical and gas-related fires, e.g. CO2 or dry powder, fixed fire suppression systems such as clean agent gas, e.g. FM200, or inert gas systems, fire-rated insulation and fire stop barriers in electrical penetrations. Fire protection measures must comply with standards such as NFPA 70 EC, NFPA 72 Fire Alarm Systems Pressure, and IEC 6079-10-1 for area classification and risk mitigation. Overpressure system and monitoring. To maintain a non-hazardous classification inside the analyzer house, an overpressure ventilation system is used to keep internal pressure above external ambient pressure, preventing ingress of flammable gases. Continuous monitoring of differential pressure is mandatory, with failure triggering safety actions. The overpressure protection system should include redundant pressure transmitters for reliability, alarm generation on low pressure condition, typically 25 PA, automatic disconnection of general purpose power, interlocks to hold energization of electrical equipment until safe pressure is confirmed. System design and operation must follow IEC 1679-16, which outlines the principles of using artificial ventilation and overpressure protection in explosive atmospheres. Emergency shutdown and electrical isolation. Emergency shutdown systems must be available both locally, manual emergency stop push buttons, and remotely via DCS-SIS commands. Shutdown procedures should safely isolate power to all non-intrinsically safe devices, stop HVAC and sample handling systems, secure analyzer sample lines, maintain power only to safety-critical systems such as gas detectors and emergency lighting. Power isolation systems must be clearly labeled, easily accessible, and capable of handling locked-out conditions for safe maintenance. Alarm and annunciation systems. All protection systems must be supported by visual and audible alarm annunciators. Alarms should indicate gas detection levels, low and high, overpressure failure, ventilation or HVAC system malfunction, fire detection activation, electrical failure, or power supply issues. Alarms must be visible both inside and outside the analyzer house with redundancy for critical systems. Alarm logic must follow fail-safe principles, ensuring that loss of signal or power defaults to a safe state. Annunciators should comply with standards such as IEC 6007-3, coding principles for indicators and actuators. Safe venting of hazardous gases. All analyzer houses must include provisions for the safe venting of process gases. Sample vents, purge vents, and analyzer exhausts must be routed to a safe location outside the shelter, protected against rain and insects. Pressure rated and constructed of compatible materials, fitted with flame arresters or knockout pots where required. If sample gases are flammable or toxic, vent lines must be continuously purged or monitored and routed to flare or safe atmospheric release points, with consideration for prevailing wind direction and personnel exposure. Emergency lighting and egress. In case of power loss or emergency evacuation, analyzer houses must have emergency lighting with battery backup, minimum 90 minutes autonomy, clearly illuminated exits and signage, manual override for doors or hatches, egress paths kept free from obstructions. Design must comply with applicable sections of IEC 600364, NFPA 101, Life Safety Code, or equivalent local standards. Routine testing and validation. All protection systems must be tested at regular intervals, with results recorded and audited. Testing should include gas detector bump testing and calibration, verification of fire alarms and annunciation, functional test of shutdown interlocks, overpressure system integrity and failover, ventilation flow and failsafe performance. Documentation of these tests supports compliance, improves operational readiness, and informs maintenance strategies. Conclusion: Analyzer house protection is not optional. It is essential for the safe and sustained operation of process analyzers in hazardous environments. Integrating gas detection, fire suppression, overpressure control, electrical isolation, and alarm systems ensures that both equipment and personnel are protected against foreseeable hazards. Compliance with international standards and routine testing are the foundations of a high-integrity protection strategy that aligns with modern industrial safety expectations. Online Analyzer Tutorial Part 7. Utilities and Facilities. Purpose and Overview. Utilities and support facilities form the operational backbone of analyzer houses, enabling the functionality, safety, and maintainability of the analyzer systems. These provisions are not part of the analyzer instrumentation themselves, but they are critical to maintaining the environmental conditions, sample preparation, power reliability, and serviceability necessary for continuous and accurate measurements. Utility systems include power, instrument air nitrogen, cooling water, sample return systems, and calibration gas supplies, among others. These must be specified, sized, and installed in line with the analyzer system's process and operational requirements. Proper planning and integration of these utilities during the design and installation phases ensure the analyzer house operates efficiently, supports routine maintenance, and complies with environmental and safety standards. Instrument air supply. A clean, dry, and reliable instrument air supply is essential for the operation of pneumatic actuators, sample conditioning components, and purging of certain analyzer systems. Instrument air should conform to the requirements of ISO 8573-1, typically class 2.2.2 or better, meaning a dew point below 0.40 degrees Celsius, oil content less than 0.1 milligrams per milliliters, and particle size under 1 millimeters. The air supply system should include filters and dryers, pressure regulators at distribution points, non-return valves to prevent backflow, flow indicators for air consumption monitoring, shutoff valves for maintenance isolation. Instrument air is often used for sample line purging, valve actuation, or as a carrier gas for certain analyzers. Pressure and flow requirements must be matched to each analyzer type and should include redundancy where applicable. Power supply and electrical utilities. Electrical power must be available in both normal and uninterrupted forms. Dedicated power circuits are required for analyzers and signal processing units, sample conditioning systems, heaters, pumps, chillers, HVAC and ventilation equipment, gas detection and alarm panels, lighting, general and emergency. Uninterruptible power supplies, UPS, should be used for critical loads such as signal transmitters, communication devices, and safety systems. All power must be properly grounded and protected with overcurrent devices and surge suppressors. Electrical facilities must comply with international standards such as IEC 60UZ 364 for low voltage installations and IEC 6111 for measurement and control equipment. Calibration gas systems' accurate and traceable calibration is vital to analyzer performance. Calibration gases, often certified gas mixtures, must be available for periodic zero and span checks. Key system elements include high-purity gas cylinders with regulators, flow control valves and rotameters, changeover manifolds for multiple gas sources, pressure relief valves and check valves, safe routing of calibration gas lines to the analyzer panel. All calibration gases must be traceable to international reference standards and stored securely in ventilated areas or gas cylinder cabinets outside the analyzer house with lines routed through gas-tight seals. Nitrogen supply. Nitrogen is commonly used for purging sample lines, protecting optical analyzer components, or providing an inert environment within enclosures. Supply should be via high-pressure cylinders or a nitrogen generation system with pressure regulation and flow control. Nitrogen systems must include clearly labeled lines and isolation valves, vent routing to safe discharge points, purge timing logic where automatic purging is used. Care must be taken to avoid oxygen deficiency hazards, especially in enclosed spaces, and gas detection systems should be used where large volumes of nitrogen are present. Sample handling and return systems. Many analyzers extract samples from process lines and must return them safely to the process or dispose of them appropriately. Sample return systems should prevent backflow into the analyzer, minimize pressure drop and dead volume, be constructed from compatible corrosion-resistant materials, use flame arresters or knockout pots when handling flammable vapors, include sample cooling where return lines are temperature sensitive. Sample disposal to atmospheric vent should be avoided unless gases are inert and non-toxic. Return to the process is preferred, routed through dedicated manifolds with proper back pressure control. Cooling and heating utilities. Some analyzers or sample systems require cooling water or electric heaters to maintain sample integrity. Cooling systems may be air-cooled, water-based, or glycol-chilled and must be selected based on ambient conditions and heat load calculations. Heating elements such as sample line trace heaters or enclosure panel heaters must be temperature-controlled with thermostats, be compliant with explosion-proof or intrinsically safe standards where required, include over-temperature protection and fail-safe logic. All heating and cooling equipment must be clearly marked, fused, and regularly maintained to prevent failures that could impact analyzer accuracy or safety. Drainage and effluent handling. Drains must be provided for HVAC condensate, sample overflow or flushing, calibration gas vent traps, safety showers, and washdown areas if applicable. Effluent must be directed to appropriate containment systems, such as oily water separators or chemical neutralization tanks, before being discharged to site drainage or wastewater treatment systems. Drain lines should be constructed from compatible materials and routed to avoid cross-contamination. Facilities for maintenance and access. Facilities must also support safe and efficient maintenance, including lockable storage for calibration equipment and consumables, local tool storage and workspace, gas cylinder handling aids, trolleys, clamps, lifting devices, adequate lighting and power sockets, emergency eye wash stations, and first aid kits, as required by risk assessment. Clearance must be maintained around all equipment for servicing, and analyzer panels must be labeled with identification tags, signal references, and utility connections. Environmental protection. Utilities must be protected against environmental degradation. For example, air intakes must include filters and weather hoods. Utility lines exposed to sunlight must be UV resistant. Metallic components must be corrosion protected in coastal environments. Utility system enclosures should have IP65 or higher ingress protection. Regular inspection and preventative maintenance are necessary to ensure that utilities remain functional under all operating conditions. Conclusion. Utilities and facilities are indispensable for supporting analyzer house operation. From clean instrument air and reliable power to safe calibration systems and sample handling infrastructure, these elements ensure that analyzers function with precision and consistency. A well-engineered utility design, aligned with international standards and best practices, not only safeguards measurement quality, but also enhances system availability, operator safety, and long-term maintainability.